what I want to do is I want to just finish the discussion that we started last time. So let us remind ourselves of where we were. We have these objects which are eigenstates of L squared so eigenstate of L squared, which is also at the same time the eigenstate of Lz. So we have this stuff. Then we looked at some set of useful operators. These L plus or minus Lx plus or minus I Ly, which obviously implies that if you are interested in Lx, for example, it's just 1/2 of L plus plus L minus, right? The Ly's cancel and you get 2 Lx when you add them up. So that was that. And then we looked at the matrix representations of these things. How do I find the matrix representation of this L plus and L minus? Just remember that if I act with L plus on Lm, I get same L, but different M, and there's also some constant that I have to put in so that everything is normalized. So I have L plus 1 minus M plus 1, and then H bar, L M plus 1. And if I operate with L minus, which is now the lowering operator, Lm is going to give me again H bar, because it's an angular momentum, has angular momentum units, and something which is very similar, L plus 1 minus M minus 1. So again, just remember that if L equals M, I am supposed to get 0, because that's the maximum Z component I can get, and I have L M minus 1 here. And last time we started out finding matrix elements associated with Lx. So what we did was we first looked at L plus. So L plus was associated with a matrix which has an H bar in it, and because it's L plus, we had only upper diagonal terms, so diagonals are 0, square root of 2, square root of 2, 0, square root of 2, square root of 2, 0, right? So that's what we had for L plus. For L minus, L plus is only upper diagonal, thank you. And L minus is the lower diagonal, so H bar 0, 0, 0, root 2, 0, 0, 0, 0, right? Then since Lx is 1/2 of these things, these I'm going through somewhat rapidly because we did this algebra last time. So what do? I just add these things up and divide by 2. So when I divide by 2, I get square root of 2 over 2, which is 1 over the square root of 2. So L plus is something which looks like 0, H bar over root 2, H bar over root 2, then 0, 0, 0 on the diagonal, H bar over root 2, 0 on this corner, h bar over root 2 here, right? Okay, so that's our Lx. Okay, so let's find its eigenvalues and eigenvectors, okay? So why am I interested in this? Because these will represent the result of a measurement, okay, in which I measure this Lx, okay? So remember our scenario, we have this general psi which comes in, and I first measure L squared, and I pick out the L equal to 1 component, okay? So it may have other pieces, okay? So all of these things that I am writing here for L plus and L minus, they are for the L equal to 1 case, right? So again, over here for the L equal to 1 case. Remember that for L equal to 2, I get a different matrix, okay? And so on. So, okay, so I now take this and carry out a measurement, okay? If I, for example, carry out an Lx measurement, then I'm going to get here eigenstates of Lx, which correspond to, okay, total angular momentum 1. So let me write them out explicitly. L equal to 1, mx equals 1. Or L equal to 1, mx equals 0. L equals 1, mx equals minus 1. Okay, so we already derived these things for mz equal to 1, 0, minus 1, but it doesn't matter which direction, whatever direction you choose, you should get the same thing, okay? You cannot get something for the z direction and something else for the x direction. The important point is that Lx and Lz do not commute. So if I, for example, get this state, I don't know anything about what mz is, okay? So now we are going to start relating these things into one another. So now I want to find the eigenstates, okay? So these things here are eigenstates of Lx, right? So let's find them, okay? So let's find them in the matrix representation. It's usually easier to find things in the matrix representation. Okay, because we know how to find eigenvalues and eigenvectors of simple 3 by 3 matrices, right? So what do? I just subtract a lambda times identity from this matrix. So I have minus lambda, h bar over root 2, 0, h bar over root 2 minus lambda, h bar over 2, 0, h bar over root 2, okay, and minus lambda here. So this now I have to set equal to 0 to find what lambda is. What will come out as lambda? What will I get? Okay. What? It's possible values of the measurement, so what can they be?
0, 1, minus 1.
Well, you need units, h bar, okay? So it's 0 plus h bar or minus h bar, okay? Let's just see. So this is equal to minus lambda cubed, okay? All diagonals going, okay, from left to right, top to bottom, give me 0. So I now look at the other diagonals. You see I get an h bar squared over 2, okay? 2 minus sign, so it's plus h bar squared over 2 for one of them, but I also have this one, so I have another one, plus h bar squared over 2, okay? So if I now just factor out a minus lambda, there's a lambda also, right? If I factor out a minus lambda from all of this, I get minus or plus lambda squared minus h bar squared, which implies that lambda is equal to 0 or lambda equals plus or minus h bar. Okay, so that's exactly what I expect. Okay, so the next thing to do is find the eigenvectors. Again, I just take this matrix, so let's do them one by one. So I have 0 h bar. Okay, in fact, let me just factor out an h bar over square root of 2 here so that I have a simpler matrix. Okay, something like that. Now, for lambda equal to 0, what is my eigenvalue equation? Well, I'm going to normalize this eventually, so it doesn't matter what the absolute values are at this stage. So let me arbitrarily take the first element as 1, okay? And the others I take as A and B is equal to 0, okay? Lambda is 0 times the same thing, but it doesn't really matter. Right-hand side is going to be all zeros. So the first line tells me A is equal to 0, right? 1A is equal to 0. Okay, let's look at the second line. So I get h bar over root 2, right? H bar over root 2 times 1 plus b, right? Please check my algebra, is equal to 0, which means that b is going to be equal to minus 1. Okay, so I found my eigenvector. Okay, so it's going to be 1, 0, minus 1. I have to normalize it. What's the normalization?
1 divided by square root of 2.
Okay, so 1 over root 2. In fact, let me write it as 1 over root 2, 0 minus 1 over root 2. Okay, so this is my normalized eigenvector, which corresponds to lambda equals 0. Okay, it's the one which corresponds to this guy here. Okay, so this is associated with the ket vector, which is L equal to 1, mx is equal to 0. Okay, that's the 0 that we have here. Okay, so the ket vector associated with mx equal to 0. Okay, let's do the others. So it's, you see, not that bad. You'll be doing this stuff for Ly in your homework. So, okay, we'll just go over this and emphasize how we can use this really. Okay, so let's go to the case for, okay, for lambda equal to h bar. So this is the mx, right? This is the mx equal to 1 case. Okay? So I have h bar over square root of 2, 0, 1, 0, 1, 0, 1, 0, 1, 0, times my eigenvector. I'll again take it as 1 times A times B, okay, 1AB. And the eigenvalue is h bar, so it's going to be h bar 1AB, okay? All right, let's figure it out. The first equation is what? H bar over root 2 times A is equal to h bar, right? So that gives me A equals square root of 2. The second line gives h bar over root 2, okay? And then I have A plus B is equal to h bar times A, right? So if I, no, this is 1 plus B. right? 1 plus b is equal to h bar times a. So h bar times a is h bar times square root of 2. So if I cancel the h bars and multiply by root 2, 1 plus b is equal to 2. So b is equal to 1. All right, so this is now my new eigenvector, 1 square root of 2, 1. What's the normalization?
1 divided by 2.
Okay, 1 over 2, right? And so this is 1 plus 2 makes 4. Square root of 4 is 2, so 1 over 2. So let me write this, in fact, as 1 over 2, 1 over square root of 2, 1 over 2. Okay, so this is my normalized eigenvector associated with the eigenvalue lambda equals h bar. Okay, so this is L equal to 1, mx equals 1. Okay, so normally we wouldn't write L equals this and m equal to that if I am working in the basis where I'm using the eigenvectors of LZ. Okay, if I don't put any mx equals something, but if I just put 1 here, it's assumed that it is the z component of the angular momentum. Okay, so z is something that we take as default. All right, so let's just finish this. So what happens when I have mx equal to minus 1, which means lambda is equal to minus h bar. So just the same algebra, h bar over root 2, 0, 1, 0, 1, 0, 1, 0, 1, 0, times 1 times a times b is equal to minus h bar times the same thing, 1 ab. Okay, so when I'm doing this algebra, I'm using the first line and the second line, but the equation, of course, must be satisfied also for the third line, right? Why am I never worrying about that?
Can you repeat the question?
Okay, when I'm using these things, when I find the A and the B, I use the first line of this matrix equation. Then I use the second line, okay? And I never worry about the third line. Why do I not worry about the third line?
The third line is the same as the first one?
Yes, but it could be different, right?
Yes, well, it is not linearly independent.
Yes, okay, so when we just take this matrix and evaluate its determinant and set it equal to 0, what we are saying is that these equations are no longer linearly independent, they are linearly dependent. So if you use 2 of them, the third one is an equation which depends on the previous 2, so you are going to get the same thing, okay? No matter what the rest of the equations are. Okay, so let's just go on. The first line again gives me h bar over square root of 2, okay, times a is equal to minus h bar, right? So a, okay, so this means that canceling h bars, a is equal to minus the square root of 2. The second line gives me h bar over root 2, 1 plus b is equal to minus h bar times a. So minus h bar times a is plus h bar times root 2. So again, this just says that 1 plus b is equal to 2, or b equals 1. Okay, so I get finally the eigenvector 1 minus root 2, 1. Same normalization, right? 1 over 2. So I end up with 1 over 2 minus 1 over square root of 2 and plus 1 over 2. Okay, so now this is associated with L equal to 1, but mx equal to minus 1. Okay, so I found all the eigenvectors of this system. Okay, yes?
How do we know which eigenvector is associated with the eigenstate?
Okay, it depends on the eigenvalue, right? So over here, okay, so over here the eigenvalue is minus h bar. Okay, so that corresponds to mx equals minus 1, right? Okay, so because we know that these m values give us the z component, well, in this case, the x component of the angular momentum. Okay, so we get eigenvalue equal to plus h bar, 0, or minus h bar. Yes?
Also, why we can't say that they are just equal to, instead of associated, I mean, L1 mx minus 1 doesn't, we just said associated with the eigenvector. Why we didn't say it is just equal to
Equal to what?
these two vectors?
Oh, okay, because they are in different spaces. Okay, so this is in the Hilbert space. Okay, so this is a vector in the Hilbert space. This is a space. This is a vector in this matrix space. Okay, so they just do the same sorts of things, because remember that in Hilbert space we have these, in general, state vectors which describe the state of the system, but you can also carry out the whole algebra using linear algebra, okay, using these vectors. But formally, these are different stuff, okay? For example, if I look at the bra version of this, so if I look at L equal to 1, mx equal to minus 1, okay, so that's the bra version of that. How do I find that? Well, that's going to be the transpose and complex conjugate. So since it's all real, it's 1 over 2 minus 1 over root 2, 1 over 2, okay, which corresponds now to this vector, okay? So basically there's just one-to-one correspondence with what's happening in this matrix and this Hilbert space. Okay, so in this case, since we have a discrete set of states, the Hilbert space vectors look very much like, okay, vectors that you have in linear algebra, eigenvectors of the matrix. Okay, but in general, of course, these things could be functions. Okay, those things can be related to wave functions, in which case they will be infinite dimensional. Okay, and the variables forming a continuum. Okay, other questions? Okay, let's just move on. So let's return back to our experiment. Okay, so before we even do that, let me just say, remember that for any of these original operators, Lz, for example, this was associated with a matrix which is diagonal, right? Because we are now working, all of this is in the basis, okay, of the operators L squared and Lz. So in their own basis, these operators are all diagonal. So remember we had this h bar, 0, minus h bar. Okay, so these are the possible values of the eigenvalue. And we have this diagonal matrix. Okay, so we have something like this. So you can easily see that the eigenvectors here are very simple. So if I just take, for example, this eigenvector 1, 0, 0, that's immediately going to give you this plus h bar, right? So this is associated with, okay, now I'll write this M11. Okay, so it is the eigenvector, eigenstate, corresponding to L equal to 1. So this is L equal to 1. So this index is L. It's always L. But if I am not specifying it, it is just M, which is equal to mz. Okay, so M, if I don't specify any direction, the default is that it's in the z direction. Okay, that's just convention. So the second eigenvalue, which is okay, so this corresponds to lambda equals h bar. If I look at lambda equals 0, that's 0, 1, 0. So if I multiply the matrix with that, I get 0 times the same thing. Okay, so when you are working in the own basis of the operator, since the operator is diagonal, it's very easy to find what these eigenvectors are. Okay, so finally lambda equals minus h bar is 0, 0, 1. Okay, so this is going to be 1 minus 1. Okay, so these are all z eigenstates of the z operator. Okay. So you see, obviously they are orthogonal to one another. We did not check this, but you can easily check that the eigenvectors that we found for things like the Lx eigenvalue equal to 1, Lx eigenvalue equal to minus 1, these vectors are all orthogonal to one another, right? So if you take an inner product, 1/2 gives you 1/4, 1/2 gives you 1/4, so you add them up, it's plus 1/2, but then you also have a minus 1/2. Okay, so all these eigenvectors are orthogonal to one another. Okay? So what we are really doing pictorially is that we have now these states of the system. Okay? So the system may be in a certain state, let's say psi, and we have this orthonormal basis. So the orthonormal basis, I can describe this vector either in terms of the eigenstates of Lz, which will be things like 1, 1, okay, 1, 0, 1, minus 1. Okay, so these are now the basis vectors. So I can describe this psi as a linear combination of these three vectors, right? They are orthogonal to one another. And so that means that I'm going to get this psi. Okay, how do I do it?
By multiplying the transpose conjugates.
Well, okay.
Inner product.
Well, I just introduced my identity. That's the way I like to do it. Okay, so identity times psi. So what is identity? Identity in this case is made up of these states. So it's going to be 1, 1, 1, 1 plus 1, 0, 1, 0 plus 1 minus 1, 1 minus 1, right? So that's my identity. This whole thing is my identity operator. So this is just like the unit vector stuff that we discussed earlier. So this takes something like the x component, but multiplies by the unit vector in the x direction, takes the y component, multiplies by the proper unit vector, etc., and psi is still there. So I'm going to take the inner product of psi with each one of these vectors. That will give me the expansion coefficients. Okay? So once I get the expansion coefficients, I have the expansion ready. Okay, it's written in terms of that. Okay, let's see. Or what I can do is I can now go to another coordinate system. So I'm just going to draw these things arbitrarily. These are probably not very accurate, but okay, I have these three again. Okay, orthonormal sets of vectors. Okay, so these are the red vectors. They are in 3 dimensions. Okay, they are again orthogonal. And these things are now, okay, L equal to 1, but mx equal to 1. Okay, L equal to 1, mx equals 0. L equal to 1, mx equal to minus 1. So I could also expand my psi in terms of these things. How do I do it? This time I write my identity in terms of those basis vectors, right? So let me attempt to write this. Okay, so alternatively, I can write this as, okay, 1, this is going to be messy, but we'll go through it. Mx equal to 1, 1 mx equal to 1. Okay, so now I'm specifying it, so it's not mz, but it's mx. So it's these vectors that I have here, plus, okay, L is 1, mx is equal to 0, 1 mx equals 0, plus 1 mx equals minus 1, 1 mx equals minus 1. So this is also identity. Okay, it's identity in a different basis. Okay, and then I still have my psi. So I can expand my psi in any orthonormal basis that is convenient for me. Okay. All right, so now let's do our experiment and see what happens. Okay. So now okay, so let's look at our experiment. Okay, so here comes an electron in some general state, and I do an L squared measurement on it. So I measure the total angular momentum. Okay? What are the possibilities? Well, I can get L equal to 0. I can get L equal to 1. I can get L equal to 2. I can get lots of different possible values for the angular momentum. Now, from those that I have measured the angular momentum, so I choose the track, okay? I choose the beam that's coming out with L equal to 1. Okay, so in this beam now I have 1, but I don't know what the z component is for these things. Now let's suppose we measure Lx. Okay, so here's my measurement for measuring Lx. So I'm now measuring the x component of the angular momentum. What are the possibilities? Well, they are the possibilities are the eigenvalues of the Lx operator. Eigenvalues of the Lx operator are, okay, h bar, 0, or minus h bar. Okay? So now, an electron, for example, going on in this state is in L equal to 1, mx equals 1 state. If it is moving here, it's in total angular momentum equal to 1. Okay, the total angular momentum itself is, remember, not equal to small l, but it's L times L plus 1 times h bar squared, right? But we call that the L equal to 1 state. And then mx is equal to 0. So there's no angular momentum component in the x direction. Or I can have, okay, and total angular momentum 1, but mx is equal to minus 1. Okay, so I get either h bar 0 or minus h bar, and this is how I label those states. Okay, so mx is 1, 0, minus 1. Multiplication by h bar is, okay, implied. All right, is this clear what we are doing? Okay, now we have another experiment here. Now I want to measure the LZ of any one of these things. Okay, so let's look at one of them. For example, suppose I take this beam and feed it into the LZ experiment. Now, how do I, okay, so what are the possibilities? Well, the possibilities for LZ is similarly whatever I have here. That's the same set of eigenvalues. So the possibilities are, again, h bar, 0, and minus h bar. So you see, no matter which direction you look at, the possible values of angular momentum that you can get for any component are these things. And it doesn't even have to be x or y or z. You can choose any strange direction in space, okay? And you are again going to get those three possibilities, okay? Because the space doesn't know what you are calling x or y or z, okay? You just measure the angular momentum in any direction. You are going to get those three possibilities. But now to find the probabilities, okay, so what comes out here is, remember, 1, 1. This is 1, 0. This is 1, minus 1. So if I'm not specifying the direction of the m, it's assumed to be in the z direction, okay? So the default is the z direction. Okay, so this is the 1 mx equal to 1 state, right? So this state here corresponds to, okay, now where is my m equal to 1 state? Let's see. Okay, so this is the lambda equal to 0 state. Lambda equal to 1 state is hidden over here. So let me just copy that over here for you. So this is going to be 1 over 2, okay, 1 over square root of 2, 1 over 2. Right? Now I want to expand this in terms of eigenstates of LZ. What are the eigenstates of LZ? Well, they are 1, 0, 0, 0, 1, 0, 0, 0, 1. So it's very easy to expand this in terms of that, right? So now you tell me, how much of 1, 0, 0 do I need? So I'm going to need that. I'm going to need that, plus I'm going to need some 0, 0, 1. So how much do I need over here? 1 over 2, 1 over root 2, 1 over 2, right? So we could have obviously calculated them by using our procedure here. What would we do? We would take the Hermitian adjoint of this and find the inner product of that with that. But you can see that it will immediately give you 1 over 2, right? Take the adjoint of this, multiply by that. What do you get? 1 over square root of 2, and so on, okay? So in this case, we can just do it by inspection. By just looking at the equation, we can see that, okay, those coefficients are just these numbers over here. So what we have written here is really 1 mx equal to 1 is equal to 1 over 2, 1, 1, plus 1 over root 2, 1, 0, plus 1 over 2, 1, minus 1. Okay. So I have just written that equation. This is in the, okay, space of the matrices, in the matrix representation. Here I am writing it in terms of the kets. Yes?
Professor, so the coefficients corresponds to probability, but okay, but so for this case, shouldn't we say that mx is equal to 1 and l is equal to 1, right? For these cases.
Mx is equal to 1, L is 1, yes.
So how is there any possibility that mz is equal to 1 or minus 1? Because the total probability should be 1, right?
Yes, total probability is 1. Okay, so what's the probability, for example, getting 1, 1? It's the square over this. Okay, so
How?
the probability is 1 over 4, right? The probability for this is 1 over 2, and probability for this is 1 over 4 again. So the probabilities, if you add them up, it's just 1.
Yeah. Of course, but mx is equal to 1 is predetermined, and total probability is 1. It is also predetermined. So how mx is also 1? Is it? Yeah. I understand the mathematics behind it, but I couldn't understand intuitively.
Well, it's difficult to understand intuitively because this is mx is the angular momentum in a different direction. Okay, so I have the, okay, so if I'm trying to measure angular momenta in x, y, z coordinates, okay, so I have x and y and z, okay, and it's given that the angular momentum in the x direction is the maximum that it can be, but there's angular momentum also in other components, right? So if I now try to measure the angular momentum in other components, I no longer know what mx is, right? Okay, so remember that Lx and Lz do not commute. Okay, so Lx and Lz are incompatible. Okay, so they are not zero. So I cannot really know both of them at the same time. Yes, okay, so if I now know, I start with an object whose x component of angular momentum I have measured. Now, if I make a different measurement here, I am now losing that information about what the x component of the angular momentum was. Okay, I can no longer say that, well, the x component of angular momentum is plus h bar, so how come I get plus h bar or minus h bar in the x direction, okay? Because the information about the x component of angular momentum is now lost. Okay? Other questions? Yes.
If we subsequently measure Lx and Lz and Lx again, in a way we initially get different results from the initial Lz measurement and the last Lz measurement, right? Is it possible?
Yes, of course. So if I now decide to measure at this point Lx again, okay? So if I try to take any one of these things and measure Lx, in fact, let's solve that problem also if we have time, not really. But if we solve for what Lx is going to be, then we have to expand this eigenstate, okay, in terms of the Lx eigenstates. Okay, so for example here, so Okay, so this is an important case, so let's just discuss it a little bit more carefully. Suppose I take this case, in this case it's, okay, L equal to 1, M equal to -1 state, and I measure, okay, Lx again. I can no longer say, well, I measured Lx already, so it should be the same, because there's an incompatible measurement in between. So that measurement, that information is now lost. So what I have to do here, over here, now I have to expand this 1 minus 1 in terms of C1, 1 mx equals 1, plus C2, 1 mx equals 0, plus C3, 1 mx equals -1. Okay, so I have to make this expansion, and magnitude squares of the C1, C2, C3 will give me the probabilities for these cases. Yes?
So in that case, can we say our measurement process in a way introduce some kind of a torque to the system?
Well, okay, torque or something else. Okay, there is some influence that has occurred so that we do not know the previous measurement anymore. Okay, so you can look at the details of how that happened. It depends on how you are measuring it, perhaps the measurement equipment, etc. But you definitely know that the information will be lost because LZ and LX do not commute. Okay. Let's see. Okay, 2 minutes. Let's see if we can look at this case. Let's take this case and make an LZ measurement again. So possibilities are H bar, 0, minus H bar. Okay, you see, you can generate a very rich set of measurements here. Measure Lx, then measure Ly, measure Lz, then measure something else, etc. Do all of these things. I recommend very strongly that you exercise on this. That will give you the intuition, okay? It's difficult to understand this just by looking at one example and trying to deduce any type of logic out of it, okay? So this is the logic of quantum mechanics, and the way you absorb it and the way you just develop intuition about these things is to solve lots of problems, okay? So if you solve lots of problems, then you start to realize that, okay, things happen one way or another. So what is mx equal to 0? Where is it? Okay, it is, let's see. Where is it? Okay, so it's the one, okay, so this, remember, was 1 over root 2, 0, minus 1 over 2, okay, minus 1 over root 2. So this is equal to what? Well, there's 1, 0, 0. Let me, for completeness, write everything. 0, 1, 0, plus 0, 0, 1. Okay, so this is, remember, the 1, 1 state. This is the 1, 0 state, and this is the 1 minus 1 state. So what are the coefficients that come in front of these things? Okay, square root 1 over square root of 2, 0 minus 1 over square root of 2. So the probabilities, you see now I get 0 probability, okay, for Lz equal to 0, and probability equal to 1/2 for this measurement, probability equal to 1/2 for that measurement. Okay, so that's how this thing works out. So you see, you now also have some predictive power in case you want to do this experiment, okay, on your own, in your garage, whatever. Okay, so I'll see you guys on Thursday.